In this video, I will present some nonlinear latent growth models. So the most common one is the quadratic growth model, and it can be used to model growth that accelerates, such as this one, or growth that decelerates over time, this one. The difference, it would be that uh, in the terms of the quadratic shape, a positive mean of the quadratic shape indicates acceleration. A negative mean of the quadratic shape indicates deceleration. So this is how a quadratic latent growth model looks like. Um, it is accomplished by adding one additional factor the to the linear latent growth model. So here we have three latent factors: level, also known as intercept; linear shape, also known as slope; and the quadratic shape. The level indicates, in this case, the initial status, because the loading here of the linear shape is zero at the first time, so we know that the level is the status at the initial time. Then the linear shape indicates really a growth with loading 0, 1, 2, 3, 4. And the quadratic shape has loadings that is the square of the loadings of the linear shape. So the loadings of the quadratic shape is 0, 1, 4, 9, 16. And you can see that um, it is a simple extension. We just add another latent factor. Now, at the bottom here, we have the model. So the quadratic model is the observation y for individual I at time t is a function of the level or intercept, which is a predicted value for time equals 0. Then we have the factor loading of the slope. By the way, the factor loading of the intercept is here, but it's not shown because it's always 1, right? Uh, so we have the factor load of the slope and the individual slope here, um, which is the instantaneous rate of change when time equals 0. And then we have the quadratic shape, which is the acceleration, plus a residual. I should note that each individual um, will have a level, linear shape, and quadratic shape. This is the quadratic model in covariance matrix format. So we have here the observed variance covariance matrix is equal to the variance covariance matrix of the linear, the intercept, the linear factor, and quadratic factor, which is here, pre-multiplied and post-multiplied by the matrix of factor loadings. So here we have the matrix of factor loadings, and here we have the transpose of the matrix of factor loadings plus the residual matrix. So we are interested in estimating the covariance matrix for the factor. So here we have the diagonal, we have the variance of the intercept, variance of the linear shape, variance of the quadratic shape, and then of the intercept, we have the covariances between them. Now at the bottom here, we have the mean structure. So this model says that the means of the observations at each time point are a function of the factor loaded matrix times the mean of the intercept, the mean of the linear shape, and the mean of the quadratic shape. Now, the coding of time for quadratic models follows the same rules as the coding time of linear models. Um, you can code it so that you can define the intercept at different occasions. So in this first coding here, the intercept is defined as the status at the first measurement occasion. The second one, the intercept, is the status at the last measurement occasion. And this other one, the intercept, is the status at the third measurement occasion. So this is exactly the same as you would do with a linear model. Okay. Now we can have other functions. So for example, if you want a cubic function, um, which is when there is like a band of growth, like there is a acceleration and then a deceleration, you would add another factor. So you would have four factors: uh, linear intercept, linear shape, quadratic shape, and cubic shape. And the factor loadings would look like this, and the model would look like this. So that is how it's specified. Now you can have more complicated shapes than this, but these are rarely used. So another variation is the piecewise growth model. The piecewise growth model is when you have a linear growth that changes trajectory. So here you have one slope until time 3, and then a different slope after time 3. This model, this type of data is common when you have an intervention over here occurring at time 3. So it could be a treatment effect, or it could be a historical event. So this model is very helpful, for example, to study the effects of interventions using latent growth modeling. And this model is also specified by adding another factor to the linear latent growth model. There are two variations on it in terms of how you code the factor loadings of the first and the second linear shapes. So in the first variation, here we have here the intervention that happens between times 3 and 4, right? So here the loadings of the linear shape are coded 0, 1, 2, and then after that they become 2, 2, 2, meaning the growth that happens up to here, it becomes constant and just because it stays over time. And then an additional amount of growth is added. So the loadings of the second linear shape are 0, 0, 0, 1, 2. Therefore, that additional amount of growth is added to on top of the growth in the previous one. Now, for this specification here, it's actually a misnomer to call this middle factor a linear shape, because you see it goes 0, 1, 2, 2, 2, so it's not really linear. Okay. Now, a second specification is to do the middle linear shape, an actual linear shape, 0, 1, 2, 3, 4, and then the second linear shape starts after the transition. So something happens here, and then the second linear shape picks up with 1, 2, right? So this one, the interpretation of the second linear shape is the amount of growth above and beyond what you would expected from the first linear trajectory, right? And that's different from the top model, because the top model, there is an interruption of growth here and a switch. I prefer the bottom one, but they are exchangeable. You know, the results can be converted from one to the other. And they're mathematically equivalent. Therefore, you get exactly the same model fit, regardless of which one you use. Now, we can also have freely estimated time points. This is when you don't know what the trajectory is for the data, and you estimate some of the factor loadings of the slope to detect from the data what the growth trajectory is. Now that this cannot be done with 3 time points because the model is not identified, but with 4 or more time points you can do it. So this is an example here with 5 time points. Um, so the loadings of the intercept are still fixed to 1 as they should be, but then the loadings of the slope are fixed to 0, 1, and then after that they're freely estimated, which means there is an asterisk here. Um, and that allows you to estimate a nonlinear trajectory that is defined from the data. Another way to specify the same model is to fix the first one to 0, the last one to 1, and then freely estimate the middle ones. And that indicates that, and that will give these loadings will become the proportion of growth, right? So if the second load is estimated as 0.3 and the third load as 0.7 and the fourth load is 0.9, it means that there is the total growth from kindergarten to spring fifth grade is 100%, but then there is 30% of that growth happens between fall kindergarten and spring kindergarten, and then another, and then 90% happens to spring to third grade. So this type of specification is more convenient to interpret, although I did find that the one where you just 0, 1 and freely estimate after that is easier to estimate